Ramesh, 15 BBT 0034. Today I'm going to be talking about the Compton effect. Arthur Holly Compton in the year 1923, he proved the quantum nature of light. This was earlier proved by Albert Einstein through his photoelectric effect.
The photoelectric effect states that light is made up of individual discrete photons that carries a quantity of energy which is directly proportional to the frequency of oscillations of that light. Arthur Compton too reconfirmed Einstein's theory by proving the quantum nature of light. He directed short wavelength electromagnetic X-rays at free stationary electrons and examined the collision between the two. Obviously, the scattered photon had lower energy than what it had initially, as it gave some of its energy to the electron as kinetic energy. Let's look at the diagram to understand what I said properly. Here we have the incident photon with wavelength lambda, and when it hits the stationary electron, the photon scatters and the wavelength changes to lambda dash. This wavelength is greater than the incident wavelength. The stationary electron gets kinetic energy and starts moving. Incident photon has energy E and momentum P. The stationary electron has energy ME c² and momentum 0 as the stationary electron is at rest. The moving electron has energy EE and momentum PE. The scattered photon has energy E dash, which is reduced energy, and P dash. The momentum is P dash. So the scattered photon makes an angle with the x-axis theta. The moving electron makes an angle phi with the x-axis. So according to the law of conservation of energy, E initial is equal to E final. So the initial energy of the photon E plus the initial energy of the electron ME c² is equal to the final energy of the photon E dash plus the final energy of the electron EE. Now let's resolve the components of momentum. So here we have P dash. This will be P dash sine theta and this is P dash cos theta. This is PE cos phi. This is PE sin phi. This is P. According to the law of conservation of momentum, we have the x and y component. So Px initial is equal to Px final. P plus 0, as this has 0, is equal to P dash cos theta plus PE cos phi. This can also be written as P minus P dash cos theta is equal to PE cos phi. Let's number this as 2. Along the y-axis, the initial momentum is 0 for both. So we have 0 plus 0 is equal to P dash sine theta minus PE sin phi. This also means P dash sine theta is equal to PE sin phi. Let's name this as 3. Now squaring and adding equations 2 and 3. P square plus P dash square minus 2PP dash cos theta is equal to PE square. Also we know that E equal to C square P square plus M square C power 4. So EE square is equal to C square PE square plus ME square C power 4. So from equations 1 and 4 we get P plus ME C square the whole square minus E dash the whole square equal to EE square. So a minus b the whole square is a square plus b square minus 2 b. So EE square is equal to C square PE square plus ME square C power 4. So on simplifying, we get 1 by E dash minus 1 by E is equal to 1 by MEC square into 1 minus cos theta. Since E is equal to hc by lambda, this can also be written as lambda dash by hc minus lambda by hc, which is equal to 1 by MEC square into 1 minus cos theta. Lambda dash minus lambda is equal to h by MEC to 1 minus cos theta. Lambda minus lambda dash is equal to del lambda, and this is called the Compton shift. We know that this factor is positive, so lambda dash minus lambda is positive. This implies that lambda dash is greater than lambda. So the scattered photon has greater wavelength than the initial wavelength. This also implies that the energy, the energy which got scattered is lower than the initial energy. So the final equation can be written as delta lambda equal to lambda c, which is the Compton wavelength. H by MEC can be written as the Compton wavelength into 1 minus cos theta.
Thank you for watching this video.